Hello students, very good afternoon. I welcome you to this this would be fifth session in the series of lectures of rotational dynamics. Okay, and this is second last lecture of this session, and in today's lecture we will be covering principle of conservation of angular momentum, and we will discuss about rolling. Okay, so without losing any further time, let me share my screen with you people. Okay, so here we go. So principle of conservation of linear angular momentum. Okay, so we have already discussed something called equation of moments, right? Equation of moments were nothing but tau net external was equal to dl by dt. Okay, like rate of change of angular momentum acting on a system will be equal to net external torque on that system. Okay, about so whenever we are writing this equation, we must realize two things. Like first thing is in what frame we are writing this equation, and the second thing is in about what point we are writing this equation. Okay, so whenever we are talking about the frame, the center of mass frame has uh, edge over other frame of references because this angular momentum in center of mass frame does not depend upon the choice of point. About any point, the angular momentum would be same. So we need not worry about the choice of point if we are working in center of mass frame in order to write the angular momentum. Whereas in order to write the equation of net torque, net external torque in center of mass frame, okay, about an axis passing through center of mass as well, if we choose the axis to be passing through center of mass, we need not worry about any torque produced by the pseudo force also. We have seen such examples in previous classes. So whenever it is possible to use center of mass frame about an axis passing through center of mass, we will be doing that, and it will be simplifying our calculation. So this is nothing but equation of moments. Okay, and conservation of angular momentum is nothing but a little bit improvisation in that. Conservation of angular momentum, I must say, it simply says that if left hand side of this equation is equal to 0, that is if tau net external on the system is equal to 0, then dl by dt, that is rate of change of angular momentum, would be 0 as well. So that means angular momentum of the system is going to be a constant. Okay, with respect to time, that simply means that due to some change before and after that change, let's say initial angular momentum of the system is li, and that will be same as angular momentum the system uh, after the change. So this is nothing but principle of conservation of angular momentum. But we need to understand, like before applying conservation of angular momentum, we must make sure that the axis about which we are applying conservation of angular momentum, about that axis, net external torque must be equal to 0. Otherwise, this will not be applicable. So this is principle of conservation of angular momentum, and that was the theory. And now let's move on to some simple questions. So question number 1 here I have chosen for you people, a very simple one, and with the help of this problem, okay, we will be looking at like how the problems look like in say ground frame, and how the problem look like when we deal it with in center of mass frame. I will be doing this problem in two different methods. One will be in ground frame and another will be center of mass frame. So here is the problem. So let's say we have a rod, uniform rod of mass m and length l. Okay, and we have another particle of same mass, let's say, and it is, let's say, moving with velocity u, and this is the line of movement of this particle. And after some time, as you see, that it is going to collide with one of the extreme of this rod in the direction perpendicular to rod. So this is the condition, let's say, before collision. And once this is given, we are required to find out the condition after collision. Mainly we are interested in like what would be the angular velocity of the rod. And let me specify here, like let's say this is a perfectly inelastic collision. So after the collision, this particle gets stuck to the end of this rod. So now then we are interested in finding out the angular momentum of the system, or angular velocity of this rod after the collision over here. So like the first method, method 1, I will be doing this problem in ground frame. So the condition after collision will look something like this. So this is the rod, the particle m will get stuck here, and this rod is of mass m and length l. The center of mass of the rod would be somewhere here. Okay, and the center of mass of this whole system would be somewhere here. This point c is the center of mass of this whole system. That means the particle plus rod system. Okay, because they have equal masses, this distance is going to be L by 4 over here. So now we are interested in that what would be the angular velocity of this system. So angular velocity, we can write it about any point. So let's say it is better to always write it about an axis passing through center of mass. So let's say the angular velocity of this particle rod system is omega, about an axis passing through center of mass, and let's say uh, the center of mass will be having some velocity v just after the collision. So this is the condition after the collision, and we are interested in finding out v and omega. In order to find out v, finding out v is rather simple. We simply would be looking to write the conservation of linear momentum only. So conservation of linear momentum, simply on this system we can see that the net external force is equal to 0. Only during the collision they will be exerting force on each other, so that will be counted as internal force. So that will not change the linear momentum of or angular momentum of the system. Okay, so since there is no external force, we are very well ready to apply conservation of linear momentum. We can apply, and we can also apply principle of conservation of angular momentum about any axis we please in the ground frame. So conservation of linear momentum will give us that linear momentum of the system before the collision, that is simply going to be mu, and linear momentum of the system after collision. After collision, this whole system of 2m mass and its velocity of center of mass is v. So simply solving this v, you will be getting it as u by 2. So calculation of v was rather easy. Okay, and in order to find out omega, we will be looking to apply principle of conservation of angular momentum. So about which axis, about which point we must be applying principle of conservation of angular momentum? Any point is good to go. Let's say this point O or this point C. All these points are good in order to calculate the or apply the principle of conservation of angular momentum here. So the better choice would be, like I said, always the axis passing through center of mass. So we will be writing conservation of angular momentum, let's say about C. So the angular momentum of the system, this is C point here. So angular momentum of the system before collision is nothing but this distance I have already seen, that L by 4. So that is going to be m times u times L by 4, and that will be equal to angular momentum of the system after collision. So angular momentum of the system after collision, we can write, like in yesterday's class we learned to write uh, how to have an expression for angular momentum if a body is undergoing combined translational and rotational motion. So one would be a rotational angular momentum and another would be translational angular momentum. So translational angular momentum about point C of the system will be equal to 0. Okay, because that component MRC, let me write it in detail so to avoid confusion. So let's say simply write final LF. So in order to avoid confusion, this LF thing is going to be uh, L tilde plus M RCOM cross VCOM. So here RCOM, you can see that this term is equal to 0. So this is going to be 0 over here. So only we are interested in L tilde, which would be rotational angular momentum. So this rotational angular momentum, you can see, would be simply equal to I times omega. So I, the moment of inertia of this rod particle system about C times omega, and IC we can calculate. IC would be simply the moment of inertia of this rod about this point C. So that would be according to parallel axis theorem. That would be ml square by 12 plus m times l by 4 square. So that is ml square by 16. So that is the moment of inertia of a rod about point C, and similarly moment of inertia of this particle would be ml square by 16 over here. So that I think will give 5 by 24 ml square. So basically here we can write 5 by 24 ml square into omega. So that gives us basically the value of omega will be equal to 6u by 5l. So omega we have got, and we previously got V also. So the what would be the condition after the collision we have found out. So this problem we approached in center of mass frame, in ground frame. So similarly we can do it in center of mass frame also. The condition before collision in center of mass frame will look like this. Say this is the rod and this is the particle. So in ground frame it was moving with u velocity. So in center of mass frame this will look like it is moving with u by 2 velocity, and this is moving with u by 2 velocity. So this is how it will look like in center of mass frame. Okay, this is the condition before collision, and the condition after collision will be simply this would be the rod and the particle will stick here, and this would be the center of mass. So it will the velocity of center of mass in center of mass frame will be equal to 0. So here it will only be rotating about this point, let's say with angular velocity omega. Okay, so this is condition after collision. So in C frame, we need not worry about about which axis we are writing the conservation of angular momentum. So conservation of angular momentum will simply, let's say about this point, let's write. So that will be equal to m times u by 2 into L by 4 plus, that is the angular momentum of this particle, and the angular momentum of rod would be m times u by 2 into L by 4, same, and that will be equal to angular momentum of system after collision, that is going to be equal to I moment of inertia about IC omega. So IC we have already calculated. So that is 5 by 24 ml square into omega. So in fact, we have got the same relationship, and this would be omega. We will be getting it as 6u by 5l. Let's try to find out one more thing in this question over here. And this problem statement is, say after the collision, we have already found out the condition. Okay, let's say in ground frame we are looking at. Okay, so this point here is moving with velocity u by 2 already we have got, that is v, and this is undergoing rotation omega, and the value of omega was 6u by 5l. So now the problem statement is, let's say let's divide this rod into two equal halves. Let's say this is O and this is A and this is B, and let's say this point is C. So O point divides this rod in two equal halves, upper half and lower half. Now I want to find out like the force exerted by upper half, that is AB or AO on BO. Okay, so what is the force exerted by the upper half on the lower half? So this is the lower half. So if we want to find out the force experienced by the lower half, the only force that it is experiencing is the contact force from AO, from the upper half of this rod itself. Okay, so in order to find out the force on it, we are going to apply apply force equation on this part OB. So on OB, we need to apply this relationship. F external is equal to mass times acceleration of center of mass. So the mass of this system of OB, like mass is basically m by 2, and in order to proceed further we need to find out the acceleration of center of mass of the section OB. So here, like this point here would be, let's say C dash would be the center of mass of the lower half. So in order to find out that, look, we need to find out the acceleration of this point C dash over here. So how can we do that? So now see, like see, this point C has zero acceleration because the net external force on this whole rod is equal to zero. So acceleration of rod AB is going to be equal to zero. So this C point has zero acceleration, and this point C dash, you can imagine it to be under moving along a circular path centered at C. So C dash will have only, you can say, centripetal acceleration. So its acceleration, centripetal acceleration, AC, or simply that would be ACOM, that would be towards C, that will be equal to omega square into L by 2. And omega square L by 2, omega we already know, so that is 6u by 5L square into L by 2 over here. So ACOM we have already got, and the force would be simply mass, that is m by 2, and acceleration, that is 6u by 5l square into L by 2. So we have been able to find out the force exerted by the upper half on the lower half over here. Calculation you can do by your own. Okay, so this is basically magnitude of the force, and this force is directed towards C at this instant over here. So this was one problem where we had application of principle of conservation of angular momentum. So now let's learn about one another concept. Okay, let's learn about angular impulse. We have already learned about linear impulse, so this is time to learn about angular impulse. That is a vector quantity as well. J, I am putting it as symbol. So J, angular impulse, is defined as tau dt. Okay, an integral of that. Okay, just like a linear impulse was defined as integral of f dt, angular impulse would be defined as tau dt over here. Okay, and this would be equal to, this is known as angular impulse momentum theorem, and that will be equal to change in angular momentum. Okay, so whenever we are writing this equation, we must be clear like in what frame we are writing and in about which axis we are writing the expression for angular impulse or tau or change in angular momentum, etc. We must be very clear about that. Okay, so let's look at some problems of application of this angular impulse momentum theorem. One simple problem I want to discuss here is say we have two disks, okay, and they are, let me draw a bigger diagram here in order to have better view. So we have one disk like this and we have another disk like this, okay, and this is the common normal at the point of contact. Let's say this is C1 and this is C2. The radius of this disk is r and the radius of this disk is 2r, and the moment of inertia of the smaller disk is say I, and this is for example 2I, let's take. Okay, so we are interested in, let's say, before some initially you can say this was moving with some angular velocity, you can say it was moving with angular velocity omega. Okay, so after a long time, I'm interested in after a long time, what would be the angular velocity of the smaller disk as well as larger disk. So what would be, let's say after a long time, this would be moving with omega 1 and this would be moving with omega 2. We are interested in finding out the value of omega 1 and omega 2. So what we can say, after a very long time, there would be no relative motion between these 2 points in contact. So they will be having equal velocities. So like this point will be having velocity in this direction and this point will be having velocity in this direction. Say this is v1 and this is v2. So after a long time, very safely we can say that v1 will be equal to v2. So v1 we can simply say that would be r times omega 1, and v2 we can say that would be 2r times omega 2. So we have got a very simple relationship. The first equation, omega 1 is equal to 2 omega 2. We have got relationship between omega 1 and omega 2, but we need one more equation in order to find out the value of omega 1 and omega 2, and that we will be doing by using impulse momentum theorem or angular impulse momentum theorem, you can say. So say here this point here is moving downward. So since this is in contact with the larger disk will apply some frictional force on this in upward direction, and equal and opposite friction will act on the larger disk in this direction. Okay, so this is the action reaction pair of friction over here. So this friction will cause or exert torque on this smaller disk as well as larger disk. This friction F will exert torque on larger disk over here. So on smaller disk, if we write equation on smaller disk, the angular impulse momentum theorem would be like the torque would be F into R. So this is tau, and tau into dt, and the integral of this thing would be nothing but the angular impulse, and that will be equal to change in angular momentum in the direction of this angular impulse. So this is going to be equal to I times, since moment of inertia is I, so I times omega minus omega 1. That would be the change in angular momentum. So similarly, on, let's say that is equation number 2, on larger disk. Okay, on larger disk we can write the similar equation, and that would be same friction is acting on that, but the this arm is different. So F into 2r would be torque, and that multiplied with dt will give us angular impulse, and that will be equal to change in angular momentum. So that is going to be 2I into omega 2. So let's say that is equation number 3. So if we divide equation 3 by equation 2, okay, so what we will be getting over here is simply omega minus omega 1 will be equal to omega 2 simply. Okay, so this is so using this relationship, omega 1 we already know, that is equal to 2 times omega 2. So simply it gives us omega 2 will be equal to omega by 3 over here. So that would be answer. Omega 2 we have got, so omega 1 would be 2 times omega by 3. So that is how we could have approached this problem. So this was one problem of angular impulse momentum theorem. Let's have one another problem of same nature. Okay, angular. So this is also quite interesting problem and very regular problem I am going to discuss here with you. So let's say we have a ball, let's say solid sphere here, solid sphere of mass m and radius r, and that is resting on a horizontal surface over here. Let's say this is its center, and we apply or we push this or apply some linear impulse on it. Okay, let's say delta p at some height h from the center. And now we are interested in finding out that what should be the value of h such that this sphere begins to roll immediately after the impulse has been imparted. Okay, so how can we do that? So if linear impulse delta p has been provided, we must be able to find out. So just after the impulse is provided, what is its linear velocity of its center of mass? Let's say what would be v naught, and we would also be looking for like what would be the angular velocity about an axis passing through center of mass, v naught and omega. And condition of rolling, and we will talk more about that rolling thing, but we must be knowing the condition of rolling here would be v naught is equal to r omega. So we are looking for this condition, but before that we need to find out the value of v naught and omega over here. So how are we going to find out the value of v naught and omega? So v naught we will be finding out using linear impulse momentum theorem. So impulse imparted to this solid sphere is simply delta p, and that will be equal to, now you must think that a friction would be acting also over here, that must be impulsive as well. So see, the direction of delta p is horizontal, so normal here will not be impulsive, so friction here will not be impulsive as well. So friction, although it might be acting, but uh, it will not produce any change in linear momentum during this small interval of time when when uh, this has been hit by a q. So delta p we can simply write it as uh, delta p would be nothing but m times v naught. So v naught we have simply got it as delta p by m, that is say equation number 1. And the next equation would be angular impulse momentum theorem. So angular impulse uh, momentum theorem here would be, so like the impulse we are providing would be simply about center of mass, about center of mass. Here we are writing, so the angular impulse is delta p linear impulse into arm, that into h, and that must be equal to I omega. So I here is basically 2 by 5 mr square into omega naught, we can simply say. So, or simply omega, let's say. So omega here, rearranging this thing, the omega here would be 5 delta p into h divided by 2mr square. So that is equation number 2. So when we will be substituting the value of v naught and omega naught in the very first equation, solving this, we will be able to get h is equal to 2r by 5. So this is the position or the height from the center where we would be applying this linear impulse so that this ball will immediately begin to roll. So this is one problem. Another interesting problem let's have for angular impulse momentum theorem is let's say the problem of spinning ball hits a rough floor. Okay, so this is say a rough floor, and we have some spinning ball, let's say of mass m and radius r. We have a spinning ball which is spinning over here, so that is omega naught, and it is falling, it is gonna fall over this rough horizontal surface. Let's say just before falling, its velocity is v naught. Okay, so after this ball, just after this ball hits this rough horizontal surface, we are interested in finding out the condition after that. Okay, so so basically we will be looking at what would be the velocity of its center and what would be the angular velocity. Okay, so let's say we are interested in finding out the kinetic energy of this ball just after it hits the rough horizontal surface, and let's say coefficient of restitution is 1. The coefficient of restitution is 1 over here. So here what we can say, like the first thing we will be writing, the condition after collision, when we will be looking at, so during the collision here, this rough surface is gonna impart, I'm gonna apply, you can say there would be normal in this direction. And now this point here has a tendency to move in leftward direction. So friction here would be acting in rightward direction. And this normal would be impulsive. So that is the reason we can say the friction would be impulsive as well. And the condition of velocity, let's say, the velocity before the collision was v naught. So after the collision, let's say this would be v, or rather say in upward direction it would be, this is normal, and the velocity after the collision, this would be vy, and this would be vx of the center. And apart from that, it will begin to, like, its angular velocity will also change to omega. So we are looking for vy, vx and omega. So how are we going to do that? So first of all, we must understand that this vy is going to be equal to v naught. That we simply can say, because the coefficient of restitution is equal to 1. Okay, so if we apply the a linear impulse momentum theorem along y-axis, this will simply give us, that would be n dt, and integral of that. So this would be nothing but impulse due to normal in vertically upward direction and change in linear momentum in vertically upward direction. You can say m times vy plus v naught, and vy we have already got, so this will be equal to, let's say, 2mv naught. So say this is equation number 1. Similarly, there would be linear impulse due to this friction also. So what we can say, that is f dt will be equal to change in linear momentum along horizontal. Initial velocity of this ball along horizontal was 0, so this is going to be simply mvx. So that is equation number 2. And now we must also be writing angular impulse momentum theorem. So this friction is going to produce impulsive torque about C. So that is going to be, torque would be F into R, and the angular impulse due to this would be FR dt integral, and that must be equal to change in angular momentum about an axis passing through center of mass. So that would be I into delta omega. So I is 2 by 5 mr square, and delta omega you can say that is going to be omega naught minus omega. So these are the three equations over here. So using I think equation 3 and equation 1, using equation 3, from 3 and 1, this will simply give us omega is equal to, let's if we divide over here equation 3 by equation 1, so that will be giving us fr by n would be equal to 2 by 5 mr square into omega naught minus omega divided by 2m v naught over here. So like this r will get cancelled over here, this m will also get cancelled over here, and f by n, let's say a coefficient of friction is for instance, let's take an example, that is mu is equal to say 0.2. So f by n will be equal to simply mu. Okay, so mu is equal to, like this relationship you can write. So solving all these equation, mu let's say is 0.2, and that would be equal to, you can say that would be this 2 and this 2 will get cancelled. So 1 by 5 uh, omega naught minus omega into r by v naught we will get. So using this expression over here, so we will be able to get the value of omega here. So solving for that omega, we will be simply getting it as v naught by r. And similarly, vx we will be getting if we divide equation 1 by equation 2, and the value of vx after solving, Vx we will be getting it as 0.4 V naught over here. So Vx, Vy and omega all we have got. So if we wish to write down the kinetic energy of this ball after the collision, so there would be translational kinetic energy as well as rotational kinetic energy. Translational kinetic energy is going to be half m times vx square plus vy square, and we have calculated the value of vx and vy. And rotational kinetic energy would be half into moment of inertia, that would be 2 by 5 mr square into omega square. Value of omega we have already calculated. So this is one problem when a spinning ball bounces from a rough floor. So if the floor is rough, this example is very good example where we are having friction, changing the linear impulse, linear momentum as well as angular momentum over here. So this is very good example. So we had a few problems in conservation of angular momentum and impulse momentum theorem, etc. Now let's start our discussion of rolling. Rolling. So first we will take the case of pure rolling. Say we have a round object, okay, which is rolling on the floor. Okay, let's say this is its center. Okay, so after some time, if it is rolling, then its center of mass will have some displacement. Let's say after some time, the center of mass, let's say, will reach somewhere here. Okay, and the sphere, say, will be like this. This is the next instant. So now you see, so when this has rolled over, you must realize, okay, so there would be displacement of its center of mass. So let's say this is x or xc or x naught. Okay, so this is the displacement of its center of mass, and at the same time it will be having angular displacement. Let's say, for example, the point P, which was previously over here, due to this, it will move somewhere here. So this point P has basically traveled this much distance. Okay, this has angular displacement, let's say theta. Okay, so this is theta. So for pure rolling, you can see for pure rolling, this distance, this length, and this length must be equal. Okay, so here for pure rolling, we can say this distance is x naught, and this distance over here you can say that will be equal to r theta, where r is the radius of this round object. So x naught is equal to r theta. So this is the condition for pure rolling. That is when there is no slipping at the point of contact. So if we differentiate both sides with respect to t, we will be getting a relationship between linear velocity of its center of mass and angular velocity. So v naught will be equal to r omega. Okay, and if it is accelerated rolling, okay, if it is accelerated rolling, then v naught and omega will be changing with respect to time. So when we will be differentiating both sides with respect to t, we will be getting a naught is equal to r alpha over here. So these three relationships, okay, collectively you can say the condition for pure rolling. Okay, so let's try to study the dynamics, or first of all let's study the kinematics of this pure rolling over here. Okay, so let me use the same diagram rather than drawing some other diagram here. So let me use other color pen. So say this is x-axis and this is y-axis, and I want to find the locus of this point, okay, which initially was the lowermost point of this round object. I want to find out the locus of this point as a function of time t. Okay, so this point, let's say after time t, when the displacement of its center of mass is x naught is equal to say v naught into t, this point has moved here. This point has moved over here. Okay, so I want to find out the locus of this point. Okay, so x coordinate of this particle we want to write, and y coordinate of this point we want to write over here. So obviously, first of all, so this is going to be x coordinate and this is going to be y coordinate. So this x coordinate basically would be this distance, which is nothing but v naught t, which you can say r omega t also, minus this. So this is r, and this would be r sine theta, and theta you must see will be equal to omega t. So r omega t minus, you can say, r sine omega t. So basically this is r times omega t minus sine omega t over here. So this is the x coordinate of the particle as function of time. And similarly, we can have y coordinate of the particle as function of time. So this is going to be simply, this distance is r cos omega t, and this whole distance is r. So y coordinate is going to be r into 1 minus cos omega t over here. So this is x and y coordinate. Okay, we are also interested in finding out the velocity along x-axis and velocity along y-axis of this point. So here we have already learnt about that also, but using some mathematics differentiation we can do that as well. So that would be simply dx by dt. So this would be r, and omega t would be simply omega, and that would be omega cos omega t. Okay, so we can say r omega, that would be v naught into 1 minus cos omega t, you can say. And similarly vy, we can simply write r omega sine omega t, which is nothing but v naught into sine omega t. Geometrically also we can see that, like, see, this particle will have two component of velocity. Let me use some any other color pen. Color, let's say this. So this particle, this point has a translational velocity, say v naught, and this has a rotational velocity v naught as well. Okay, so here the velocity along x-axis, if this angle is theta, this would be theta as well, and this here would be theta as well. So velocity, so this component here become v naught cos theta, and this component has become v naught sine theta. So you can say when you will be taking the resultant along x-axis, the velocity is v naught minus v naught cos theta. So that is v naught into 1 minus cos theta, which is this relationship. And similarly along y-axis, it is v naught sine theta, which is v naught sine omega t. And similarly you can write down the acceleration as well. So acceleration is ax and ay. Just by differentiating, you will be getting v naught omega into sine omega t over here, and this will be simply v naught omega into cos omega t. So v naught omega is also omega square r, and that would be sine omega t, and that would be omega square r cos omega t. Okay, so this is the idea. So ax and ay we have got. So we have got already the any point on the periphery if we are having. So we got their coordinates as function of t, velocities as function of t, and acceleration as function of t as well. So if we wish to draw y versus x plot, okay. So the equation of x and y we have already in parametric form. Let's write that again. So here x is equal to r omega t minus sine omega t, and y is nothing but r into 1 minus cos omega t. So this locus we have got as parametric form. So when we will be plotting it, okay, this will look something like this. Okay, and this form is basically known as cycloid. So the locus of the point on the periphery would be cycloid. So if this point was initially touching the ground, and then after one complete rotation it will touch the ground again here. So this is if it is at t is equal to 0, this would be t is equal to 2 pi by omega, and again it will touch at t is equal to 4 pi by omega, etc. And in one complete rotation, the horizontal displacement it will cover, if it is x is equal to 0, so this is going to be x is equal to 2 pi r, this is going to be x is equal to 4 pi r, etc. And this you must understand, the point uh, can rise maximum along y-axis by 2r over here. Okay, so like basically we using this relationship as a function of time, you will be able to get x as well as y coordinate at any instant of time. One another thing we are interested in, that what is the distance covered by any point in the periphery during one complete revolution. So let's attend to this problem. So let's say this is the sphere, this is the round body, and we are looking at this particle, and let's say this angle is theta is equal to omega t. So the velocity of this point is basically, this is v naught, and this is v naught here as well, due to translation and rotation. So this angle theta, so this angle basically is theta over here. So the resultant velocity, I must say, or the speed here, the speed of this particle, I must say, will be somewhere in this direction. This is v. So v would be nothing but equal to 2 v naught sine theta by 2. So this would be the v over here, 2 v naught into sine theta by 2. So if we are interested in finding out the distance covered, so like v is varying as a function of theta, and this is 2 v naught, and theta is function of time, so that is omega t by 2 over here. So small distance covered in time dt, we can simply write that would be v dt, that would be 2 v naught sine omega t by 2 into dt over here. So the total path length covered during one complete cycle L would be simply 2 V naught sine omega t by 2 into dt. Okay, and its integral from for one time period, let's say from 0 to 2 pi by omega. And solving this, we will be able to get it as that would be 8 times V naught by omega, which is basically 8r. Okay, so 8r over here. So this is quite an important result, that L will be equal to 8r. That would be the distance covered by any point on the periphery, okay, during one complete rotation of the rolling body over here. So that is also very, very important result. So let's proceed with the kinematics of the rolling here also. So we have already learned that if this horizontal surface is stationary, okay, and this, the velocity of its center is v naught, and it is moving with omega, so v naught is equal to r omega. We have already understood. So now let's look at this problem a little bit differently. So let's say we have a plank which is moving with velocity, let's say v1, and here we are having this velocity, let's say, as v naught, and this is omega over here. So here what would be the relationship between v1, v naught, and omega? Another way of looking at the rolling is simply, you must understand, see, since we are saying that there is no relative motion between the point of contact, let's say there is a point A on the sphere and point B on the ground, and they are in contact with each other, so no slipping simply means that VA is equal to VB. So VA, we have already learned, it will have, due to translation, velocity V naught, and due to rotation it will be having R omega. So velocity of point A can be written as V naught minus R omega, which will be equal to VB, which is equal to 0. So this way also we are getting the condition for rolling. So this is looking at this thing a little bit differently, and we can apply the same logic over here. So let's say this point is B over here, and this point is A over here. So for no slipping at the point of contact, that is for pure rolling, VA got to be equal to VB, and VA, let's say this is V naught and this is R omega. So VA is going to be V naught minus R omega, and that will be equal to the velocity of point B, which here this time is equal to V 1 over here. So basically we have got this new relationship. So, or you can say R omega is equal to V naught minus V1. So this relationship, or you can say this is V naught 1. Okay, another similar looking example we can have. Let's say we have some plank here, we have some round object here, and we have a plank at the top. Okay, so let's say the lower plank is moving with velocity v1 and the upper plank is moving with velocity v2. Okay, and we wish to find out like what would be the velocity of center of mass. This is what would be v naught and what would be its angular velocity omega. So that is, I think, very simple question. So first of all, what we can say that these are 2 points in contact. So for rolling, these points must have same velocity. So this point will be having velocity v naught minus r omega, and this point will have velocity v naught plus r omega, and this point has velocity v1 and this point has velocity v2. So two relations, since there is no slipping at this point of contact, v naught minus r omega, we can write it as v1, and there is no slipping at this point of contact, so we can write v naught plus r omega is equal to, we can write it as v2. So here, by solving this equation number 1 and this equation number 2, v naught we will be getting, that would be v1 plus v2 by 2, and omega we will be getting it as say that would be v2 minus v1 by 2r over here. So this is the looking at the kinematics of the rolling a little bit differently. Okay, so now let's look at some problems of accelerated rolling, or before that, like we are left with so little time, so it would be better to, let's do it quickly. We will take some extra minutes here. So let's take the condition of accelerated rolling. I would be taking up this problem here. So let's say this is a round body and its moment of inertia, let's say, is about its center is mk square. Okay, and now a force is being applied on it in horizontally rightward direction, let's say at a height h from the center. Okay, and now I wish to find out like what would be its angular acceleration and what would be its acceleration of center of mass. Okay, if friction between this rolling body and this sphere is sufficient enough for rolling, means there is no slipping over here. So we want to find out these two quantities. So how are we going to approach this problem? So in order to approach this problem, we must understand like there is some friction acting at this point of contact, because there would be tendency of relative motion at this point of contact. So let's say there would be some friction F acting in, let's say, rightward direction. Right now we don't know the direction of friction, only we know that it will be along horizontal, but whether it would be horizontally rightward or leftward at this instant we don't know. So in order to find out the acceleration of center of mass and angular acceleration, we need to write the equation of force and equation of torque respectively. So first of all, equation of force along horizontal will simply give us capital F plus F is equal to mass times acceleration of center of mass, that is ma naught. So that is equation number 1. And the equation of torque simply gives us the equation of torque about center of mass we are writing over here. So torque due to this F would be simply Fh, that would be in clockwise direction, and torque due to friction would be minus F times R, and that would be equal to moment of inertia about center of mass, that is mk square into alpha. And condition for like alpha we can write using the condition of pure rolling as a naught by r. So that is equation number 2. So in these two equations we can see we have two unknowns like f and a naught. two unknowns and two equations. So we can very well solve for them. So the value of A naught, we will be getting it as F into 1 plus H by R divided by M into 1 plus K square by R square here. So that will be the value of A naught. And once we will be substituting the value of A naught in equation number 1, we will be able to get the value of friction as well, and this friction will turn out to be F times H by R minus K square by R square divided by 1 plus K square by R square over here. Now in the very beginning we were worried about like what would be the direction of friction, and this equation is going to tell us that thing over here. So you must understand, so in this, while writing these equations, we have assumed the direction of friction to be in forward direction. So if this quantity becomes positive, if the value of this quantity is positive, that we can say like our friction will be in forward direction, and if this quantity is negative, then we can say like our direction of friction is in backward direction. Okay, so everything is going to depend upon the sign of this thing. So sign of this thing is going to depend upon this quantity. So we can say like case 1, very clearly we can say that if H by R is greater than K square by R square, so that gives us friction is positive. That means forward direction, that would be in forward direction. And case 2, like if H by R is less than K square by R square, that means the friction is going to be negative, that is in backward direction. Okay, and the another interesting case would be basically case 3, and it might turn out like if sometimes H by R is equal to K square by R square, then simply F will be equal to 0, and that is the most interesting case because we will not be needing any friction, okay, in order for pure rolling to happen. Like for example, we have a ring, uniform ring. Okay, so for ring, you must understand like K square by R square is equal to 1. And on this ring, if we apply some force on the peripheries, so this like H will turn out to be equal to R. So H by R is equal to 1 as well. So in this case, K square by R square is equal to H by R. So here at this point of contact, no friction is required for the rolling. So even if this surface is smooth, the rolling will happen. Okay, so we will look into some more problems of accelerated rolling in the next class, like the rolling on the inclined plane. And we will also look into the problems of when we will be having slipping at the point of contact, and the rolling will begin after some time, and in those cases the friction will be doing some work. Okay, and we will be looking at the work done by friction. Okay, so here I end this session. Thank you for joining.